will tell us about the topological properties in the whole.
Okay, thanks, Val. So let me recap what we did yesterday. So we started with an operator problem, the problem posed by and solved by Matsuno. So we had an operator, a wave operator, and he computed the whole spectrum of the operator. So here the spectrum. Spectrum is the dispersion relation, this one, plus the polarization relation that we described. And so this was this dispersion relation. An important information in this dispersion relation was there's a spectral flow index. So this n, which is +2, 0, -2. And I insist on the fact that this is a particular example found in geophysics. Yes? So the polarization relation is the relation between the different fields for a given solution. If I take this point and I want to plot the solution, I will plot the meridional velocity field, but also I will need to show you what is the height field and what is the zonal velocity field. And those three, if you know one of them, you know the two others. And this knowledge is given by the polarization relation. And this is because we had a multi-component wave problem. So three fields, 3 components. So is an operator described by a matrix that I wrote last time, a matrix of operators. And here, yesterday, I showed you first a simpler case posed by Kelvin, where F is constant, here F was varying, so it was an operator with spatially varying coefficient, which is very important. In Kelvin problem, we had really a matrix where the coefficients are just a real number, a complex number. So we have, and this is what I call the bulk problem. And here, the interface. Interface because we have a spatially varying parameter appearing in the wave operator. Bulk because we considered a problem with the same dynamical equation, but constant parameter. And the solution are just plane wave solution. And at the end, to find the polarization relation in this problem, we have to diagonalize a matrix. This is what Kelvin did. And what I said yesterday is that in this simpler problem is encoded an information that is related to this spectral flow index. And this information will be topological here. And there is a theorem that links this topological information to this spectral information. Now, in this example, this is a specific geophysical case, but this is a very, I want to stress that this is a very generic situation in physical system when you have several fields with several wavebands, with gaps within the different wavebands. And when some of the parameters are varying, you have interface, and there may be trapped mode along the interfaces as those modes here. So the object we want to describe here is a collection of eigenvector, the polarization relation. For each point here in a parameter space, I have 3 solutions corresponding to the 3 eigenmodes: the positive Poincaré frequency eigenmode, the negative Poincaré inertial gravity wave eigenmode, and the geostrophic mode. So I will consider one of them and denoted psi, and the 3 vectors will be u, v, and eta. Okay, I will drop the index plus that I put yesterday, that to say that I refer to the positive Poincaré frequency eigenmode. And I say that there is one particular point in the bulk problem where the waveband, there is no sense to speak about the waveband because they touch each other. This is a 3-fold degeneracy point. Okay, and we want to describe an object given by a a surface in this parameter space, and on each point of this surface, we will look at those eigenmodes psi, which are normalized eigenmodes, which means that they are defined up to a phase. Okay. You can make a choice of phase here, take one, but I can make another choice. And I want to describe this object. I have a collection of vectors that can be twisted, and I want an information that does not depend on this phase choice, because it is arbitrary. Yes. Yes. This is confusing. I agree. Yes. Yes.
The mapping is still.
Yes, but in this three-dimensional case, actually, we can make as if they were on this space. I will come back to it, because actually, I will start. I will need this. Okay, no. I will. So now I will be. I will come back to very basic things about topological objects. So remember topology. From a physicist perspective, it is just that what allows us to classify objects into families. And what I said yesterday is that I gave the example, for example, of a sphere. There is no handle, no hole. So we say that the genus G is 0. We could take a donut, torus. Here, the genus is 1 because there is one hole, one handle, so on. So this is an integer number that characterizes the family of objects described by no hole, one hole, and we can deform one object into another one, and they will belong to the same family. Okay, first thing. So then there is another integer number that is related to this one, which is called Euler characteristic. And this is something that Descartes and Euler noticed, is that if you deform whatever surface, closed surface like this into a polyhedron, or like this, do this continuously, and then you can define a number K, which is the Euler characteristic, which is also an integer, which turns out to be 2 minus the genus, so it's related to the genus. And what is amazing is that this formula was noticed by Euler by defining the Euler characteristic as the number of vertices of those shapes. The number of face, let's say minus the number of edges plus the number of vertices. So you can check it. It works. And as an exercise, do it for the torus. There is a little trap. So if you're bored at some point, it's a lecture game to check this formula for the torus. What I want to point is that we have two very different definitions. Here is the number of holes. Here is something related to the property of polyhedron, and they are connected together. Then, okay, that's one thing. This will play, those kind of numbers will play an important role in the following. And another thing is that there is a formula, the Gauss-Bonnet formula, that relates a topological quantity of members of different family, here the Euler characteristic, to a geometrical property that depends locally on the property of the surface. Okay, so this formula states that the Euler characteristic is 1 over 2 pi, the integral of the Gaussian curvature integrated over the surface. So I remember you, the Gaussian curvature is you take this sphere or whatever patatoid, this, you take a tangent plane at some point, and then you look at different direction in the tangent plane, and you look at the curvature along those directions. There is a maximum, a minimum. You multiply those two curvatures, minimal, maximal, gives you the Gaussian curvature. This is this K. And this is really amazing because you can deform your initial sphere. This K will change locally. It can become here, it's always positive, but you can make saddles, it will be negative, meaning that at some point there will be stronger curvature to satisfy this equality. So this is a really nice and impressive formula that relates a global topological properties to local geometrical property of surfaces. So now I said that the objects we want to describe are not just surfaces, but collection of vectors on the top of surfaces. So it's a simple example is to take those surfaces and look at tangent vector to the surface. So here, in that case, they live in the same space. We'll take just a sphere, say a planet, and look at the wind at the surface of the planet. And let's keep the color code. And there is a theorem, loosely called the Hairy-Ball theorem, or Poincaré, that say that if you look at a field of tangent vector to the sphere, let's say they are all normalized, there must be a singularity, and it's possible to characterize this singularity by an integer. So here, the way I draw the vector field, there are two singularities, one here and one here. And I can look from above, from the top of those singularities. So it's a zoom. This, a zoom from the top, and it looks like this. Zoom from below. This. And you can take a circle here, a line, and you look at how the vector rotates when you travel along this line. This defines a winding number, and this is +1 in that case, +1 in that case. Okay, and you probably saw those indices, those winding number in the lecture on last week on topological defects. So those are topological defects, kinds of topological defects. And the point here is that there are two indices that are positive, and they are actually given by the Euler characteristic of the surface in that case. So what we did in mathematical terms, what I did when I drew this field of vector is choosing a section. I have a rule. I look at tangent vector to the sphere, and I want them to be normalized. I make a choice of directions, and with this choice, my two singularities are here. I could make another choice, and I would remove those singularities. I could create them by pair of +1 and -1 singularity, but the total sum will be always 2. So we can move them, we can create pairs that annihilate each other, but the sum will be the Euler characteristic. So here the choice of section will be the angle of the vector in the tangent plane, each point. And now, coming back to our initial problem, here it is a bit similar, except that we are not looking at tangent vector to the sphere. We are looking at eigenmodes at each point, which are three component vector with complex numbers. And the choice I can make is not the rotation with respect to the tangent plane, but the choice of phase. So choosing a phase will be choosing a section. And I want to describe a number that does not depend on this choice. And this number, in that case, for complex eigenmode bundles, it's a bundles of eigenmodes on a closed surface. Let's call it K or Chi, I don't know in English. And but this is no more the Euler characteristic. This is now the Chern number. So really, if you hear Chern number in that case, more precisely is the first Chern number, what you have, let's have this picture in mind. It counts a number of singularity in this abstract space. And physically, the singularity, they describe twisting of the vector field, of the complex vector field. And so it's possible to define this Chern number by counting singularities, a bit like in this case. But in physics, the most popular way is to use a generalization of Gauss-Bonnet formula by Chern. It's called Chern-Gauss-Bonnet formula that relates this integer number to a curvature, which is no more the Gauss curvature, because those in those cases we are not interested anymore on the tangent fields, vector field tangent to the sphere, but on an eigenmode. So it's a vector. So let's call it a vector, but actually it's a curvature. In mathematics, it would be a two-form, but we don't care too much about this here. And n will be let's put right away the good space here, and n. I have a surface element dA and a vector normalized n. So what is this curvature? This is called the Berry curvature, at least by physicists. So this is the same Berry as the Berry with the anomalous dissipation with worms of this morning, Michael Berry. And so let's write vector that way. I will now give you the recipe how to compute it. Yes? Yes. Maybe it's confusing. Sorry about this. I should have said different number. It's the same because it's possible to put those two objects into the same family. So that's why the same term is used. Okay, what we are doing here is that we have a field of vector on the sphere, and we notice that there are singularities. At some point, you're multi-valued, the north pole and the south pole. So I could make another choice, and whatever the choice, this is a Herible theorem, you will find points that are multi-valued. Now we want to characterize those singularities. Does it correspond to a vector fields that make a 2 pi turn or 4 pi turn? So this is what we try to do by this, is look at where are the singularities, zoom at those singularities. So those two plots are zoom on the top of it, and check and then define a winding number for those singularity. So winding number is you look at the close to the singularity, you take a closed line enclosing this singularity, and along that line you follow the vector, and as you see here, the vector turns along this line. It makes a 2 pi turn here and here too. In the two cases, in one case it's divergence, in another is convergence, but in terms of phase singularity is the same. You turn, you make a complete turn. You could have more complex situation where you make 2 turns, 3 turns, and so on. Or you can have a saddle with convergence, divergence that will be -1. Yes, exactly. Yes. So Gauss-Bonnet is a way to relate the topological invariant of your family here, surface, to a local geometrical property, a local curvature of the surface. Now, the Chern number describes the singularities for more complex objects given by complex eigenmodes. Here, like this surface with on the top of it at each point a polarization relation. So this object can have singularities, and it's possible to count them. And I show you with this formula, the Chern Gauss-Bonnet formula, a recipe to count the singularity without having to make this construction to find where they are and to zoom into those singularities and to characterize them. Yes, the vector field is three-dimensional because we have three components wave problem with u, v, and eta. And it's not only three-dimensional, and each component is a complex number. So it's difficult to visualize those kind of objects. Yes? Yes. Okay. Good question. In the problem of Kelvin, I will write it. Let me write the problem solved by Kelvin, the bulk problem. It was omega psi equal 0 f y f k. I say that c equal 1. Nice. Okay. This is the Kelvin, the shallow water problem. Once you have put the plane wave on that, so you have to just to diagonalize this matrix, and you have three solutions corresponding to the three wave bands. And in this matrix problem, you notice that you have just three parameters. And this is a very important question because it will be essential to define a Chern number in those problems to find in your wave problem three parameters. It turns out that here we have the two wave number and f, because f was taken as a constant in Kelvin problem. You are in the tangent plane. We look at the rotating shallow water equation with f constant. So you can treat this as a parameter. Exactly. Exactly here in this space, this is the term, the correct term. We have family of the solution, and this family of solution is not very nice. It is twisted, and we will see how twisted it is, and we can describe this twisting quantitatively with the Chern number. This is really the idea. And one recipe to compute this is this Chern Gauss-Bonnet formula. Yes. Yes. Yes, exactly. No, I will stop with this one because I will be happy with this one because you're actually in physics. Usually, it's in many cases the Chern number is defined that way. It is taken in many cases as a definition of the Chern number. I wanted to point out that the Chern number is really related to this Euler characteristic in that sense that it describes singularities. But I will not describe this picture. But if you are interested, actually, I recommend, and in the lecture note, I gave the reference. There is a kind of lecture note paper by Frédéric Faure a couple of years ago, where he explained this point of view. He's from mathematical physics, and he was very excited when he learned about those results about topological waves. because in the 2000, around 2002, he did actually a lot of work relating the spectrum of molecular spectra to matrix problem using bulk interface correspondence. So before all the fuss about topological insulators, he was really he had a deep understanding on this correspondence, and all his understanding is applicable to those this case. So I recommend his lecture. Is on archive, and he makes the two description even for this equatorial case. This description are looking at the singularity, and this description by computing the Chern number. So let's come back to this Berry curvature. Let's write it. So I have three components that I will call Fk, Fl, Ff, but actually it's more like a pseudo vector. So I would prefer to write it like this: Fl, F, F, Fk, Fkl. And the definition is that F lambda mu, so lambda can be Kl or F, and mu can be Kl or F. K F. It's Y. So you take the conjugate transpose of your eigenmode. You derive this eigenmode by lambda. Make the scalar product standard Euclidean scalar product with the same eigenmode divided by d mu minus y psi over d mu. So perhaps it's a bit abstract that way. Let's write just one to be sure to follow. KL is in this particular case where psi is u v eta, it will be y du over du star over d lambda times dk times du over dl minus y du star over dl du over dk plus the same thing where you replace u by v plus the same thing where you replace v with eta.
Normalization condition of psi, otherwise.
Yes. Yes. I should stress this is that I consider normalized eigenmode, a family of normalized eigenmodes. And one thing you can check is that with this formula is that it does not depend on the phase choice. Okay, and perhaps to give some intuition of the origin of this formula, let's look at this eigenmode, and let's make a small small increment in parameter space. And you want to look how much has changed the eigenmode. It has turned a bit, for instance, when you went from there to there. And this is what you want to describe: local twisting, so local quantity, geometrical quantity. And if you do this, a way to do this without that is just to project your vector field, the variation of your vector field psi. So it will be I will call this dr with r a vector given by k, l, and f. I define the variation of the polarization relation will be given by A times di R with dr with A defined as you project on the eigenmode the gradient in parameter space. So R means that I take the gradient in parameter space. And you can check that F is like a magnetic field, is the curl of this potential. So this is called the Berry connection. It tells you how you change the vector, this complex eigenmode vector, when you change place infinitesimally in parameter space. And when you take the curl of this, you get, so this depends on the phase choice. This does not depend on the phase choice. And this is the Berry curvature. So now it's possible to apply this recipe because we know the expression of the eigenmode. We just have to diagonalize this matrix. And we can make derivation and compute this and integrate over the sphere. And actually, in the present case, the computation is not too difficult. And I just would like to present the results, but first, to give you a hint about the singularities by looking at K, L, F. So either I stay in Cartesian coordinate for this parameter space, or, which is quite convenient, you can go into polar coordinate. So theta here and psi. And here I have R, the norm of the vector R. And in this representation, the eigenmode for the positive Poincaré waveband. So you can do it as an exercise. So I'm not sure I will remember the formula correctly, but it's something like this: cos psi minus y cos theta sin psi plus y cos theta cos psi. The correct expression are in my notes because I'm not sure to remember. But this is the expression. And what I want to point out first, so what you can do is first you diagonalize the matrix in Cartesian coordinates. Then you switch from Cartesian to polar coordinates to get this formula, which is a nice way to see the family of vector field, because first you notice that the polarization relation does not depend on R, just on theta and psi. First thing. And second, you can see the singularity here. Actually, take theta equals 0 and theta equals pi. So it will be +1 here. And you see that at those points, the field is multi-valuated. So you have a singularity here, a singularity here. But this depends on the phase choice. You could multiply by I psi. Here, this quantity, when theta equals 0, is E minus I psi. And so those two terms will cancel. So the singularity that was here is removed. But by doing this, you will add the singularity in this line. So it's like with this case of Herible theorem, you can change your family of eigenmodes. You change the location of the singularities, but they are there. Okay. I want to point out that there is another way to see a singularity that is quite nice and that is used by Rosa and Zoe that are here. You should see their poster. Is you look at the field V as a function for a given f, v of kl times eta star of kl. This quantity does not depend on the phase because you multiply two components with the complex conjugate, so it cancels out. And this is another way to see the singularity of this object. Yes?
So in both these things, the phase is just a global phase. It doesn't vary within this case.
It varies because the phase you can choose as you want locally. So for instance, in that case, I can multiply this quantity by psi. I could take a function of theta. And so what I say now is that it's impossible to define continuously a vector field that would not be that would be single evaluated everywhere with any choice of phase.
If it was varying, so in your f lambda mu definition,
yeah,
that should show up as a derivative.
Yeah. But here you can check that whatever this choice here, this result will not change. That's an important point. So I wanted to point out that just by looking at the dispersion relation, we can see the singularity in the same way that we see the singularity here. Okay. Yes.
That should be an arbitrary.
Yes. No, it doesn't have to. I say this because with this choice one here, I noticed that when theta equals 0, here I have something that, so I'm here. I have something at this point that is multi-evaluated because I can vary phi, and I have a collection of vector at this point. So it's like this schematically. And I made this choice because then I cancel this singularity here. But by doing this, I have twice the singularity here in the other field. It's a bit complicated because we have 3 fields and the singularity can be one field in the other. But the point is that globally, this quantity, the Chern number that describes the singularity, will not depend on those choices. There were another question? Yes, exactly. Yes. Okay, so this is convenient to see the phase singularity, but actually to compute, to use this formula, if you are very skillful with change of variable, you can do it from there. But it's simpler to take the Cartesian coordinate representation of the eigenmodes, to do brute force computation of the Venaille curvature here. And when you do that, you have a very simple result that the Venaille curvature is just R over R3. Again, you can check it. So it's really like a monopole that radiates. Let's plot it in K, L, F. So we had this bond touching point. And something that looks like a monopole, a source. As if we had if it were a magnetic field, it would be like a magnetic monopole. And if you integrate this quantity, you find that 1 over 2 pi that f here, it's 2. And you can make the same computation for the middle band, the flat band, it should be 0. It's topologically trivial. So what you can have in mind for a topologically trivial state is, for instance, if you consider, I come back here to the tangent vector field to a surface. If we had not a sphere, but a torus, donut, and we, in that case, the field of tangent vector to the surface is topologically trivial. The Euler characteristic would be 0. Okay, so here we remain on the sphere, but this object for the middle band is 0. And by symmetry, once you have done this computation for the positive frequency, you can find the negative frequency. And the net outcome of the computation is that we have a Chern number. I should have called it C maybe. That would be +2, 0, and -2. So if I summarize, we had a wave problem with spatially varying coefficient with a spectral flow index that comes out of this wave problem. We have the same wave problem, but with constant coefficient and with at the end amounts to boils down to diagonalizing a matrix. What we have done is analyzing the property of the eigenmodes, which are complex eigenmodes, and is described by a topological property, the Chern number, which is +2, 0, -2. And so we note that the spectral flow index is equal to the topological index. And this is, in that case, a kind of remark that we have this equality. But there is a mathematical theorem that guarantees that it should be the case, that it is expected that we didn't have to solve the Matsuno problem. We just had to solve this Kelvin problem to compute this Chern number. And with this knowledge, without solving the problem here, we knew that these wave bands should gain 2 mod, this one should have a net gain of 0, and these wave bands should lose 2 mod. Okay, so there are different names for, so I would like to call this a bulk interface correspondence results. In condensed matter, it's called bulk boundary, but in that case, it's a bit different because there are systems where you can define a Chern number, say in the northern hemisphere, define a Chern number in the southern hemisphere, and there is a boundary in between the equator. You stack them together, and you get this result. That the number of mods that will be gained or lost, it depends on the difference of Chern number from the northern hemisphere to the southern hemisphere. Here it's a bit different because the Chern number is describes the interface itself. We are in a space with a family of solutions where we vary K, L, and F. We need to make F vary. If I take F constant here, I'm not able to define a Chern number. Here, neither. But still, we can make a qualitative interpretation of what happens as in condensed matter by saying that when we built this dispersion relation, let's start with our knowledge of the Kelvin problem. Let's take a given value of F, yeah, in the northern hemisphere, the southern hemisphere. So the dispersion relation here, remember yesterday plot was something like that. Yeah. In the southern hemisphere, for the same value of F, was something like this. And if I showed you the dispersion relation in both cases, you wouldn't be able to tell me if I am in the northern hemisphere or in the southern hemisphere. You would be able to give me the answer if I show you the eigenmodes, the eigenvectors. And this properties is encoded of the eigenvectors in this quantity. And what we did when we computed, what Matsuno did when computed this problem is kind of stack together this dispersion relation with this one. So here we have a wave band, the same here. So we may expect that the final outcome of the problem should give the same wave band. So this is the case here. Same with small deviation giving the Rossby wave that lifts the degeneracy for the central band. But what we have seen here with this Chern number, this singularity, is that if you take the family of positive eigenmodes in this plane here, KL, you have a family of eigenmodes. You change, you decrease slowly the parameter F. You change your family continuously. You are close to the equator, and at the equator, something happens. the notion of waves has no meaning. It is like a defect, a topological defect, and it is an obstruction to deform your whole family of eigenmodes, positive Poincare frequency eigenmodes from the southern hemisphere to the northern hemisphere. And the way to, when you compute the spectrum to overcome this obstruction is to close the gap by those two eigenmodes here, given by the Kelvin and Venaille mode. This is a very, very unwavy explanation. Perhaps you are not satisfied. I was not satisfied by this explanation myself, and that's why I don't know if I will have time to present this in the last lecture, but I think a way to formalize this argument is to consider ray tracing, to look at ray tracing of a wave packet at the equator, and to use quantization relation Bohr-Sommerfeld to reconstruct the spectrum, and then you get this picture of an obstruction of the equator that prevents you to continuously deform a family of eigenmodes. I will come back to this later. So for the equatorial problem, this is all I wanted to say. But now what I would like to illustrate is that we have a general method, recipe, if you wish, to relate complicated wave problem with spatially varying coefficient to a more simple, to a simpler one, where you take here the coefficient constant. So when I'm saying this, I'm very imprecise. What does it mean to take the coefficient constant? It is not an issue in this problem, but in the next problem we will look at, this will be one. So I will give you something more formal to how to switch to go from the interface problem to the dual bulk problem to be solved. But the general idea is the following. You take your initial problem, you transform it into a matrix problem, simpler to solve. You look for degeneracy points. Here there were only one at the origin. So you look for points where the bonds touch each other. And at those degeneracy points, you have a singularity that you can characterize with a Chern number. And actually, this characterization has been done by people before us, because there are classification of results of the Chern number depending on the number of the nature of the singularity. For instance, it's expected that for a threefold degeneracy point like this one, the Chern number should be +2, -2, 0. It's expected that generically for twofold degeneracy point, the Chern number describing winding of eigenmodes along this Chern number is around this degeneracy point is +1 or -1. So you even do not have to compute it. It's done. Yes. Yes, okay, it's a very important remark because I wanted to discuss this before going to the coastal problem. So your question is, can we use these results to say something to more complex profile f of y? Yes, this is important because this correspondence is expected for a generic profile of f, provided that there are here this works that way because f is increasing, an increasing function. So this is very important. I would like to discuss this. And the question is, what is really topological in the problem? So the short answer is, what is topological is this object. Okay, we say topological wave, but it is a kind of an abuse of term because there is nothing topological in the wave itself. What is topological is this object, and then there is this relation, and that makes the whole spectrum topological in the sense that the global shape of the spectrum depends on the topological property. There is nothing peculiar to the waves itself. So that's one thing. A consequence of the global shape of the spectrum is that we expect two modes that the gap. And so we expect to have within the gaps unidirectional modes. That's one thing. Here you have two unidirectional modes, but look at here. You have many modes, but still the result holds because you count the number of modes that you cross. And for each mode, you look whether the group velocity is positive or negative. You compute the number of positive of modes that going westward minus the eastward minus the modes that are going westward. You get a number which is 2. Okay? So what is topological is the mismatch, a difference between two numbers, a difference between eastward going mode and westward going mode. And then the results guarantees that you can switch from this profile, linear one, where you have computed the Matsuno spectrum, to say this one. It also tells you, and this transformation is interesting because I told you at the beginning we had track mode, and we want to explain this with topology. But I was a bit impolite then during the rest of the first lecture because there were all the. I promise you that we will explain trapping with topology, but everybody is trapped here. But what is important is that the results that you have unidirectional modes holds when you transform this beta plane into this hyperbolic tangent. And in that case, all the modes that were localized becomes delocalized everywhere. You have a sine, cosine function on each side of the interface, all the modes, but the two unidirectional modes here that will remain localized. So you will have here Kelvin and Yanai for this profile that will remain localized. So in both cases, the spectrum has the same shape, but in this particular case, the modes, the spectral flow modes that are unidirectional remains localized, while the others becomes delocalized. So this is one point. I just want to say a word about the trapping length scale. Here it was C over beta. It's called the equatorial radius of deformation. And in that case, you go from F0 to minus F0 with a hyperbolic tangent. And the length scale is called the Rossby radius of deformation is C over F. Intrinsic length scale of F0. The problem. Yes. Yes. You mean if I consider? No, you're right. For instance, okay. If I take this, so excellent question. In this case, I expect nothing. I expect a spectrum. That maybe that will be discretized. I don't know that will have this band, this band, this band, but those modes will be removed. That's a key. A second key point is that what is really important. When I say interface, I should have said that I wanted that the parameter f goes through a critical value. Here, the critical value is the equator, f equals 0. So this is really important. And this critical value is the value for which in parameter space, you have the degeneracy point. It could occur in other problems at f with a given value. So it doesn't need to be 0, but it needs to be a value associated with the degeneracy point. This is really key to this correspondence. So you have your initial problem with spatially parameter. You have the family of eigenmodes in parameter space. You look at where are the degeneracy points, and you say, oh, I cross one here, but there could be one here, and then the interface would be here. And the trapping would occur close to this point. by degeneracy point, here I mean that the bond touch each other. Here they are zero. It's because of the symmetry of the problem, but you have more generic situation where they could be non-zero. They just no. Yes, we could take something. So this is topological trivial here, in the sense that we expect no modes that cross the gap, and but then we can recover a topologically non-trivial case by doing something like that.
That figure just for pointing out that there's a difference between the two hemispheres that brings time reversals to opposite senses, whereas it's the third plot that French one does there, not the same song. So there's not qualitative. If you look at Zoe's poster on, see that she looked at basically that page that not in,
General theorem, right? We should make it easy. You have to search a 3-parameter space to find ideal classes. That's basically what happens. You can surround it with a 2-dimensional surface.
Yes, this is a very important remark. I should say it again, is that to find this Chern number, we have to be able to define a Chern number. We need a closed surface, and which means that we need to find in our problems 3 parameters to define the surface. And on the top of the surface, we look at the eigenmodes. Then we could have two fields involved, 3, 4. It doesn't matter. But what is key is that we need to have 3 parameters at hand.
I guess it's fascinating. So here F is a constant, right? You're solving a problem with translation variance.
Yeah.
Matching the problem where F is beta Y.
Yes.
I'm so a bit hazy on how you had an eigenvalue index N,
yes.
harmonic oscillator. It's somehow gone away. Instead,
yes.
Yes,
I intend to say it when I present the coastal case, because for the coastal case, I will need to do it formally with a Wigner-Weil transform. Which is the way. So the second thing is that, okay, the first thing is we need 3 parameters, because to have a Chern number, you need a surface. And the second thing is that this is expected to work for the theorem. Maybe it's more general, the result, but the theorem that exists is supposed to work for Hermitian matrices, which is the case here. Okay, you take a complex conjugate, you can transpose complex conjugate, and you recover the same matrix, and the operator, initial operator, is self-adjoint. Yes.
Can you explain why we are even for the general case? I mean, we can see that we got this spectral flow index, but maybe in this general case, it's not a state, just expect the dispersion population.
So, for instance, in this general case, why do you have delocalized mode? Well, a simple explanation is that take a constant here, then you came up with a Kelvin problem in a semi-infinite plane, Kelvin problem in a semi-infinite plane. You know that solutions are sine wave, so you have to match sine wave together. So that's why they are delocalized. But once you have done this, you have not computed all the modes. There remains 2 modes, and those 2 modes, they are correspond to the Kelvin and the Venaille wave. They get the same number of nodes in the y direction. And why they emerge? They emerge because they reflect the impossibility to continuously deform the family of eigenmodes from there to from the southern hemisphere to the northern hemisphere. This obstruction prevents you to do this. But again, I plan to show you a way to compute this spectrum from ray tracing, where naturally the Chern number emerge from the ray tracing plus quantization relation.
And from that, it would be clear word that there is a hateful.
Yes.
Okay.
So far, as far as I understand, you argued that
you have unidirectional mode because of topology, but I still don't see why that mode is localized from topological logic.
So well, it's true that from topology argument, the only thing that you get is this spectral flow index. And in fact, in that case, those ones are not, they are all localized, but the result of topology here is that the spectral flow mode, they are the lowest, the gravest mode. Okay. Well, there is one thing is that the gravest mode, remember n equal -1, n equal 0, they are those modes. So in that sense, they are more localized than the other.
But that's the consequence of your choice of f. If I change f of y to some arbitrary function,
Yes.
as long as that's one crossing, we still have the unidirectional edge.
Yes.
But the localization, like, you might not have one, right?
No. But the number of zeros will increase in the meridional direction with increase with the index, and the modes with less zeros will be the one that correspond to the spectral flow.
I guess a related question to that is if I didn't cross y, if it's just a parabola, if it just
Yes.
touches the axis and comes back, what happens?
Yeah, there is, you need to cross to go to get a topological mode, you get to go below 0. You need to cross the singularity here. Okay, so you need to be epsilon below the. But really, a last point, because I spoke about trapping length scale, but I think it is important because you can use topology to have information in the asymptotic limit where this trapping length scale is much smaller than the variation of the Coriolis parameter. I think this is really important because if you do numerical simulation, you compute the eigenmode, it's often convenient to have doubly periodic domains. And if you do this and you want to study an equator, you will take f is like this. And here your periodic, so it's the same point here and here. Okay. And so from the point of view of topology, this problem is trivial because what you do with this profile, you start from here, you go above, and you go back. So you go through the singularity in one direction, then you go back in the other direction. So one equator, this is one equator of the Earth that turns in the other way here. And here is the same equator because F is increasing. If the Earth turns in the other way, the Matsuno spectrum will be in the other way. It will be like this. Okay. So the sign of the derivative of F is important. We'll have something like that and something like this. Okay. But if you look at the spectral flow in this problem, this waveband lose to mode and gain to mode. It's topologically trivial. But still, asymptotically, you can use topology to say, okay, it's true that it is globally topologically trivial, but if my trapping length scale, it's small here. So if I have a planet of double radius A, and I have C over beta much smaller than A, remember that in Matsuno computation, the modes are localized at the equator. You can split your problem into two parts. So globally, the problem is topologically trivial. And in fact, if you zoom here, you may see that there is some hybridization of the modes and still a gap. But if you look from far and at lowest order, you separate the problem into two parts. So this is very important for two reasons. First, when you apply the bulk boundary correspondence, you need to be careful with the way you cross the singularity from below or from above. Then globally, you may be topologically trivial, but still topology can help you to interpret the spectrum because you have a global shape and you can interpret the global shape if you have separation between the trapping length scale of your problem and the general variation. This is also very important because even in trivial case, you can use topology to interpret For instance, in that case, which is topologically trivial, we can use topology separately in both equators to make the interpretation. So on the school website, I will put a Daedalus notebook where you can play with this doubly periodic equatorial case. It's thanks to Zoe, who gave her. I had an older version of Daedalus with a script. I prepared a script, but that was useless because you were learned to use Daedalus 3. And thanks to Zoe, you will have it. And I encourage you to use it, to play with the profile, to look at what happens in that case, to change boundary condition from doubly periodic to a channel case and so on.
So, I mean, in all this analysis, this is a linear analysis. Real systems have convection.
Yeah.
So, experimentally, we see that these modes don't interact. Is there a good physical reason? Because if we have convection, these modes start interacting, then I would expect these things could mix and be destroyed. Right? Physically, that's not what we see.
Okay, so I think it depends on the problem at hand, because you have remember the example of yesterday of the equatorial wave in the atmosphere. They are the modes stuck to each other. There are exchanges, but still you see a footprint of the linear analysis. So a possibility is that at lowest order, not too far from having linear waves, but then energy can be shared between mode and exchange. And this would be the approach, for instance, of weak turbulence. At lowest order of the waves, and then they talk to each other and spread the energy between the waves. And then you have a situation which are strongly turbulent, and the wave doesn't tell you much. So it depends really on the experiments you're looking at and on the parameter that controls the nonlinearities.
So I guess, like, so for the atmospheric equatorial modes, what is the dimensions number that characterizes?
I don't think I will be able to answer to why it works so well for the equator, but we'll have to check for the Reynolds number. And then for a parameter that compare the strengths of the something like the Rossby will be important too, because you want to compare the strength of the rotation to the amplitude of the mode. So an equatorial Rossby. So and also stratification play a role. So you have something like a Richardson number that compares stratification to velocity. So Reynolds, Richardson, or Rossby. It's already quite complicated. So I wouldn't be able to say where you must be in parameter space. For sure, for the linear theory to work, you need a strong rotation.
One thing, which is you could take one of these Kelvin waves and increase the amplitude so much that it can start to break. And so you see it numerical simulations distorts, but it still is a unidirectional wave pattern. So there's still something very robust about it, probably because it's in this gap. And so some degree about linearity doesn't seem to destroy this.
And related to this, if you look at those waves here, the Rossby waves that are nearly non-dispersive, and here those Venaille waves, they are also soliton. So here you have a Burger-like equation as that with weak nonlinearity, as Brad says, that is breaking. And here you have in different region of parameter space, we'll have KdV, Korteweg-de Vries-like equations that describe solitonic structure on the top. So you start from linear solution. Either you look at a collection of waves that talk to each other, wave turbulence, or you look at a specific waves, you increase nonlinearity, and then you have the physics of solitons or shocks and so on.
I guess I just would have expected, because you have these two topological waves crossing, if there's an interaction between them.
Yeah.
Like they mix, and then so you lose unidirectional. It's not linear from now.
Okay, on this point, even at linear level, if you start to mix topological from one equator with one from the other equator, even at a linear level, you will have a hybrid, how do you say this in English?
But I just remember the video, you had two waves that went like this, seemed like they just kind of went past
You mean the tides?
Yeah, yeah, yeah.
Okay, for the tides, it was different. It was coastal waves, and then there can be interaction between the coastal waves and the equatorial waves. But I'm not sure that when we saw on the video was a consequence of this. Because on the video, you have a forcing that has a structure, and we see the response to the forcing that involves a collection of modes. I just wanted to point out that among those modes, we have those trapped waves, but I'm not sure how much we can further we can go. What about the time? Okay, so I have how much time? When? Yes. No, no.
So going back to the second plot that what you think that with the that don't propagate
yes, it is a good way to see it. If you, in that case, if you put forcing here, all the modes will remain. You put forcing like convective forcing at the equator, they are all trapped. While in this configuration, if you put forcing at the equator, most of the waves that you excite will, because they are delocalized, a consequence is that if you excite them at the equator, it will flux the energy out of the equator, while those two Kelvin and Venaille mode would remain at the equator. So it's a good way to see it. Yes, and it's very important physically that for the Earth's equator that the consequence of the trapping of all the modes is important because it means that a lot of the energy remains there. Should I start with? Okay, I will not use the. I will keep the blackboard and I will just say a word about symmetries. So let's keep this. So let's write again the equation. So this is the beginning of lecture. So there will be 2 lectures in the 3 lectures, but this is fine. It will be on coastal waves. But I will start again with the equation written down for the equatorial waves, just to discuss the symmetry. Many times broken symmetry were mentioned. Brad just spoke about it. I think it's a nice time to present those symmetry. So I write again equation F C minus 3 spec minus y minus y. Okay, so what are the discrete symmetry in this problem? So let's look at time reversal symmetry. So we have time x, y, u, v, theta, and f that I will change to minus time x, y, minus u, minus v, theta, minus f. When we make this transformation, you can check that we recover the same system of equation. So this is a discrete symmetry. And this is time reversal symmetry in a classical sense. And what you notice is that if f is 0, your system is symmetric. Okay? But if you are in the northern hemisphere and if f is prescribed, you lose this symmetry because to get the symmetry, you need to transform f into minus f. And you say, I want to remain in the northern hemisphere. So when F is given, you break the symmetry. And we saw already a consequence of having F non-zero in the previous lecture. It opens a frequency gap. Okay, this is one consequence. Another consequence is that we get those unidirectional modes, which are called chiral modes because they are not the same as their image in the mirror. And I will show you another consequence of time reversal breaking symmetry perhaps right now, which is the emergence of amphidromic point in tight. I will tell you after what it is. But before this, let's look at other symmetry. You have time reversal symmetry, but another effect of prescribing F is to break another symmetry, a spatial symmetry, mirror symmetry, say in the, let's start in the right direction. So I transform X in X, T in T, X in X, Y in minus Y, U in U, V in minus V. Again, you can check that you recover the same equation with this transformation. And again, you see that if F is prescribed, you have broken this symmetry, like a parity symmetry. And when you can notice is that when you combine this and this, you apply it twice, then you change F into F. And so you recover a symmetry, which is the combination of time parity. So your system is isotropic. So in 2 dimensions, when you add Coriolis force, you do not break isotropy. It's just in 3 dimensions that it becomes anisotropic. So you have the same symmetry for the X direction. So it's T minus X, Y minus U, V, theta minus F. And you have a last symmetry, which is just related to the fact that you started with an equation describing real field. And this last symmetry, let's call it C, that would transform X, Y, sorry, T, Y, U, F into X, Y, U star, T star, eta star, minus F. So because if we impose that we have at the beginning only real field, then U star will be U, star will be V, eta star will be eta. And what you can notice is that you combine those 4 symmetry, those 4 transformation, this one, this one, this one, this one, you have a transformation that is the identity. So it's a kind of, we quote CPT symmetry for fluids that you have the identity transformation by this conjugation transformation, time, and mirror symmetry in both directions. But really, what I want to insist on is the combination of those 2 symmetries. Let's just draw a graphical representation. I insist on symmetries because there have been classification of topological insulators and more generally any physical system. When looking at the discrete symmetry that are left or broken, you may expect or may not expect to have a Chern number or another topological invariance pop up in your problem. So it is very important in that context. And let's take a planet that is rotating. This. Let's look in a mirror. Then you're rotating in the other direction. You change omega into minus omega. And let's take time reversal. This will be mx. And let's take time reversal symmetry. We recover the same set of equations for shallow water. Okay, this is the combination of those 2 symmetries. And with the 5 minutes left, I would like to describe 2 consequences of the symmetry. And I will start with the consequence on tides. Is it fine to do this, Brad, or should I wait, take question and wait for our next? Okay. So let's consider shallow water equation in a lake or an ocean. From the point of view of topology, it will be the same. And I want to look at eigenmod with and without rotation in this lake or in this ocean. So let's first consider the case where f equals 0. So you have time reversal symmetry. And I want to look at the structure of the eigenmod. And I will write eta as eta hat of x, y times e omega t plus eta star e minus e omega t. Because I get time reversal symmetry here, and I look at this symmetry, eta is transformed in eta, I expect that eta hat is a real function. It is a real function of 2 variables. We expect that generically it cancels, its amplitude cancel along lines. So if you look at an eigenmod for this problem, the zeros of the eigenmod, the amplitude, will happen along line. So it's like a sloshing, a sloshing of the modes, like you would have in a small tank. If you perturb it, to go like this. And now let's look at f different than 0. So this you break time reversal symmetry. So you break this the time reversal symmetry impose eta hat real. Now it is complex. Of course, the field itself is real because you took the complex conjugate, but this part of the field becomes complex. And because it is complex, if you want to cancel complex fields that depends on 2 variables x, y, you cancel the real part, it happens on line. You cancel the imaginary part, it cancels on line, and the line cross at points. And so it will not be the same ocean, but sorry about this. And now what you see is that you will have only cancellation of the height at specific point, and you can draw the phase line. So it will be like this. And if you look at the structure, the temporal structure of the waves, you will see that you have a rotation along those singularities that are called amphidromic points. I should say that this argument is from a paper by Venaille in the 90s. And this is very nice because those amphidromic points, you can see them on tides, on tidal maps. And they were drawn in the 19th century for the first time. There were some theoreticians that didn't believe the result of the seagoing oceanographer that showed the results. And it's often presented as the first example of a phase singularity in physics. And what is really nice, I think, related to the previous, the first part of the lecture, is that here you see a given wave mode that has a phase singularity for the eigenmod itself that comes up because of the breaking of time reversal symmetry. While in the previous example, here. We had also phase singularity. For a given section, we saw that the fields of eigenmode were multi-valuated. So on this surface, here we have the kind of phase singularity that are like amphidromic points, but in parameter space, that again are due to the presence of the time reversal symmetry breaking parameter. So we have a kind of phase singularity in parameter space here for a family of eigenmodes. But if you look at the structure of an eigenmode itself, you have in physical space phase singularity that are observed since a long time in the ocean. The next lecture, I will really start on the coastal wave because this is, I think, another example of the first case in physics of an unidirectional mode. I think Kelvin, in his paper on tides, computed the first unidirectional trapped modes, which are now called the coastal Kelvin ones. So I will take question now. Yes, yes, exactly. Yes, yes. The continent changed completely the picture. So, but about the bulge, I think this is not so wrong in the sense that you have one point if the yeah, and you have one point above that doesn't move. So you keep. I think this is pretty robust. The presence of the yes, but the structure, the global structure of the when we see the video of the first lecture, it's very confusing compared to the two bulge picture. I agree. I mean, I am confused by it. It's an excellent question. First answer, you should see the poster of Zoe because she is speaking about this. And second answer, this problem belongs to a much wider class of wave problems that not always, but in many situations break the hermiticity. This is one thing. And another thing is that another complication that is added by this is that when you do this, you add a continuous spectrum into the problem. Here, the spectrum is discrete, but as soon as you get a new flow, you get continuous spectrum with generalized eigenmodes, in the sense that you have singularities in the eigenfunction. It's called generalized eigenmode. And but this is very rich. There are many things to explore. There seems to be cases where the spectral flow correspondence seems to hold, and there are currently physicists from other fields and this field that work on this non-Hermitian generalization of bulk boundary or bulk interface or whatever name is used from non-Hermitian to from Hermitian to non-Hermitian case. And I think what is very interesting with geophysical or astrophysical fluid dynamics is that even if it is never presented with this point of view, there is a huge literature on those non-Hermitian problems from a theoretical point of view, with detailed computations of the spectra, the generalized eigenmodes. So it will probably be very fruitful to explore this line of problems. Yes. How did it change to put a quadratic velocity field in that case? Yes. I'm afraid to say something wrong, but from what I remember, there is a threshold where it couldn't become unstable when gamma increases too much, and you still get drop mode, but you can get a transition to instability. I have in mind a figure from Boyd when we see this instability and some kind of mode mixing, but I don't know much about it. Maybe Brad or Zoe has a more precise answer than me. I don't know. Okay.
One of the one remark, which is that with active matter, there's been work by the group of Martini with looking at blocking topological spherical surfaces, and now it's very similar to what Chern presented, finding waves of topological active matter.
And they had a dissipation in the top, in the area mean flow plus dissipation, and very strange behavior appears when they push the dissipation far. This is also a very interesting line of research related to this.
So at the very end, we got I'm wondering if in a very big you get the color
So we tried a bit. We wanted to find the equivalent of a Z2 invariance, because when you look at those symmetries that are broken or that are conserved, you can have a class of system described by Chern number like this, and class of system described by another invariance. But we didn't manage to. Maybe there is one. Maybe we can find one, but we didn't. So we played. Then the classification can be extended with spatial symmetries on the top with inversion, broken, clip. And playing with this, we found some particular cases that are interesting. But at the end, it's always boils down. In the case we found, different symmetries are broken, and the way time reversal or mirror appears, it's a bit hidden. But always at the end, it boils down to finding the degeneracy point, computing a Chern number around the degeneracy point. So in that sense, it's not a different class of problem. So you can split the, you have for a given problem, it might be hard to find where is the degeneracy point, but at the end, once you find it, it's the same recipe. Yes.
Sorry, I think I didn't get it. Like a wave all around.
Yes, exactly. Yeah, think of a wave doing like the tides. Okay, think of the tides that follow the coast. If you look at the tidal hours on for the coast, and one part of the coast, the tide is at a given time of the day, and another part of the same coast at another time, and there is a traveling time. And this is really what describes those. Here is the coast, and this is high tide, low tide, and this moves. So those are fish doing, and this moves, but this moves perpetually, but those points are fixed. And if you go at those points, you will never see a tide. So this is why in some region of the ocean, you can measure you can try to look at tides, but there will be no. And if there is an island here, at this part, in this island, it's at the middle of the Pacific, but you're close to the amphidromic point. There is no tides. Yes, yes. This is really fascinating. And there are studies how those tidal points, they are very sensitive to the shape of the coast. They can be moved by changing the shape of the coast. It's,
What is the
Excellent question, because I switch here from f equals 0 to f non equals 0, but here I have a typical L, and I have a typical scale again in this problem, which is the C over F, which is called the Rossby radius of deformation. And to see this, you need to have the Rossby radius of deformation much smaller than F. Otherwise, look at this picture. If your Rossby deformation is not large enough, if you have, say, a lake here, you will never see an amphidromic point. You will be in this version. So these to see the trapping of the modes, you need to have a small Rossby radius of deformation compared to the domain scale. And this is intuitive in the sense that this is what, when you decide to put your Coriolis force or not, this is what you decide if you are at large scale or at small scale. So you compare an intrinsic scale, the Rossby radius, to the scale of your domain. Yeah, I will show you a map next lecture. I will start with this to see the amphidromic points. And it is even measured in lakes, sufficiently large lakes. Okay.